All right, here we have problem set number 9, where we're going to be talking about electrons and waves, wave properties of particles and things with mass. So we've talked about light and how light is a wave, but it also has particle characteristics, and now we're going to talk about electrons, which we usually think of as particles, are in reality also behave very similarly to waves at times. So let's get started. So Louis de Broglie correctly postulated that matter has wave-like properties. What was the de Broglie wavelength of the baseball, 0.145 kilograms, thrown at 108.1 miles per hour by Nolan Ryan in 1974, the fastest pitch recorded? Okay, so we are trying to find a wavelength of a particle. This is different than finding the wavelength of light. So when we're talking about photons, we have these equations E equals h nu and C equals lambda nu that allow us to find and discuss wavelengths, frequency, and energy of photons. That is not what we're doing. Why? Because this is not a photon. This isn't light. This is a baseball. And as a result, we need to use the de Broglie wavelength equation. And the de Broglie wavelength equation says that the wavelength of something is equal to Planck's constant divided by mass times velocity of that thing. So let's talk about units real quick. Planck's constant is in joules times seconds, and since joules, so that's going to be the same as joules is kilogram meter squared per second squared, and as a result, we need to make sure that our mass is in units of kilograms. Velocity then is meters per second, and the units cancel out such that we end up with a wavelength in units of meters, which is what we're looking for. So we can go ahead and solve this problem. We know that the wavelength of the baseball is going to be equal to Planck's constant over the mass, 0.145 kilograms, times the velocity, 48.325 meters per second. And if we go ahead and do that, h over 0.145 times 48.325. That gives us a wavelength of about 9.46 times 10 to the negative 35 meters. Okay, so hopefully you recognize that's a really small number, 10 to the negative 35 meters. And that makes sense. That's why you don't see the baseball waving. It looks like a particle to us because its mass is so big. And because mass is on the bottom of the equation, a big mass will give a very small wavelength, recognizing that h on the top of the equation is times 10 to the negative 34, so that's also a very small number. So when do these wave properties of particles really start to matter? They start to matter when your mass becomes really, really small. When I'm dividing by a really small number, my wavelength gets bigger, it starts to matter, but we'll see some of that later. So, all right, assume the uncertainty of the measured speed was 5.5 times 10 negative 28 meters per second. What is the uncertainty of the ball's position as it passed the hitter? Did the fact that the ball had a wave-like properties add significantly to the challenge of hitting the baseball? All right, so this question is asking about uncertainty. Uncertainty matters because of the wave-like behavior of things. We don't really ever know exactly where they are, because, like, if I asked you where is a wave in the ocean, there's not really a location for it, right? And in reality, Heisenberg figured out that if you take uncertainty in the position of something and multiply it by the uncertainty in the momentum of that thing, m times v, that value will always be greater than or equal to h over 4 pi. So this is the Heisenberg uncertainty equation, and we can use this. We can use the uncertainty in the speed to find the uncertainty in the position. Now we're going to do something here because we know the mass of the baseball. There's no uncertainty there. We can take delta x. We can pull out the mass and just get delta V by itself. That's greater than or equal to h over 4 pi. We're not really just pulling out the mass. We're applying the chain rule from calculus, but it cancels out to that, and so that's just fine. So the uncertainty in the speed is 5.5 times 10 to the negative 28 meters per second. What's the uncertainty in the position? So we want uncertainty in the position, so I'm going to get delta x by itself. There we go. We got delta x by itself. Now I can plug everything in. So 6.626 times 10 to the negative 34 for h. 4 pi, the mass of the baseball is 0.145 kilograms. And the uncertainty in velocity is 5.5 times 10 to the negative 28. Okay, plugging all of these in. When I do that, I get an uncertainty in position. That has to be greater than or equal to 6.61 times 10, I guess only 2 sig figs, times 10 to the negative 7 meters. So did the wavelength properties make it more difficult to hit the ball? Well, first off, the wavelength is on the order of 10 to the negative 35. That's not very significant. And the uncertainty is on the order of 10 to the negative 7. So that is very likely not going to make a difference. In your ability to hit the baseball, because your eye probably can't even see that degree of uncertainty. All right, so now we're going to move on. We're going to calculate the wavelengths of the following objects. Now these are objects, not photons, and so we're going to use the de Broglie wavelength equation over and over and over again. So again, wavelength equals h over mv. In this case, a muon, we've got a mass of 1.884 times 10 to the negative 28, and a velocity of 325. Gives me an uncertainty of 1.08. Or not an uncertainty, sorry, a wavelength of 1.08 times 10 to the negative 8th meters. Okay, next one, we got an electron. Mass of 9.10938 times 10 to the negative 31. Velocity of 4.05 times 10 to the 6th. That gives me a wavelength of 1.3 sig figs, 1.80 times 10 to the negative 10 meters. Next, we've got and one thing to notice, we're talking about muons and electrons here. The wavelength of an electron is on the order of 10 to the negative 10. That's an angstrom, is 10 to the negative 10 meters. And one carbon atom is about 1 angstrom in diameter. And so you can see electrons are small enough, their mass is small enough, that their wavelength starts to matter on an atomic scale, which will be interesting as we move forward and talk about orbitals and the behavior of electrons as waves in an atom. All right, we've got an 82, I don't know why there's 2 C's here, we've got an 82 kilogram sprinter running at 9.9 meters per second. And that's going to give us a wavelength of 8.2 2 times 10 to the negative 37 meters. Big sprinter means that their wavelength does not really matter, right? 10 to the negative 37. And now the Earth, which is really big, I got a mass of 6 times 10 to the 24, a velocity of 3 times 10 to the 4. Gives me a wavelength of 3.7 times 10 to the negative 63 meters. There you have it. So those are 3 examples of using the de Broglie wavelength equation. We know we need to use that wavelength equation because we're not talking about light or photons. We're talking about objects, muons, electrons, sprinter, Earth, right? Those are objects with mass. Therefore, we need to use the de Broglie wavelength equation to find their wavelengths. All right, a synchrotron is a type of particle accelerator in which a ring of variable electric and magnetic fields accelerates particles, electrons, protons, etc., to speeds nearly the speed of light. The largest synchrotron in the world is the Large Hadron Collider in Geneva, Switzerland, where protons with that mass can be accelerated to this speed. What does this mean? This is 0.99999 whatever, 1 times the speed of light, so nearly the speed of light. What is the de Broglie wavelength of one of these protons? So, de Broglie wavelength, that's the mass, 1.6726 times 10 to the negative 27. What is the speed? How many 9s are there? 1, 2, 3, 4, 5, 6, 7, 8 times the speed of light. And when I do that, I get a wavelength of 1.3321 times 10, wow, 321 times 10 to the negative 15 meters. Okay. Oh, is that all it asks? Yep, let's de Broglie wavelength. B, what is the wavelength of an electron moving at the same speed? Okay, so that means we've got an electron, h over mv equals 9.109 times 10 negative 31. 1, 2, 3, 4, 5, 6, 7, 8. And that gives me a wavelength of 2.426 times 10 to the negative 12 meters for the electron moving at that speed. All right, if the relative uncertainty in velocity of a proton in the Large Hadron Collider is 3%, what is the uncertainty in this position? Okay, so we're dealing with uncertainty, and so we are going to be using the uncertainty equation. So we know delta x times mass times delta v is greater than or equal to h over 4 pi. We are trying to find the uncertainty in position. So delta x is greater than or equal to h over 4 pi m delta v. All right, so let's see what we've got here. We know h, 4 pi. What is the mass? Well, we're talking about a proton, right? And so they gave us the mass of the proton up here, 1.6726 times 10 to the negative 27 kilograms. That's the mass of my proton. And Now the delta V, well, it's 3%. That means 3% of its velocity. So we need to find 3% of its velocity, so that's going to be 0.03 times 1, 2, 3, 4, 5, 7. Speed of light. Okay, plug those guys in. H over 4 pi 6726 10 to the negative 27 0.03 point. Okay. I messed up something. So H over 4 over pi 0.6726 over 10 to the negative 27 over 0.03 over C. There we go. And I get an uncertainty in the position of 3.5 times 10 to the negative 15 meters. And that's the same as 3.5 feco meters. Feco is 10 to the negative 15. All right, so how does this uncertainty affect the ability of scientists to collide such a proton with an atom that has a diameter of, on the order of angstroms, 10 to the negative 10? So basically what this means is we know exactly where our proton is, plus or minus 3.5 times 10 to the negative 15 meters. That's cool. And if we're trying to hit something that its diameter is 10 to the negative 10 meters, well, 10 to the negative 10 is way bigger than 10 to the negative 15. So it's going to be pretty easy still to hit the atom. Because the atom is so much wider than our uncertainty range. But then it asks, how easy would it be to hit another proton? Its radius is 0.9 fecometers. Our uncertainty is 3.5 fecometers. So our uncertainty is, almost 4 times the radius of a proton. So it's probably going to be pretty hard to hit the proton, because the proton's radius is a lot smaller than our uncertainty in the position of our proton. Okay, so let's answer some conceptual questions. So what is the wave function? The wave function, so this is psi, and it is the solutions, or I can just say solution to Schrodinger's equation. That's an important thing to know. It's called the wave function. And it tells us defines the allowed energies electrons can have. Okay, and each wave function is identified by some quantum numbers. So what are quantum numbers? How they're related to wave function? I'm going to say that the wave function is identified by quantum numbers. It's kind of how we by quantum numbers. It's kind of how we talk about the wave functions is in context of the quantum numbers. Yep. What does the square of the wave function give us? Okay, so the wave function is like a function, like an equation, that tells us the energies that the electron can have. When we square it, we get the probability that an electron exists in a certain location. So it pretty much gives us like a probability density function that says the electron's very likely to be here, less likely to be here. Very similar to like if we have a normal curve, let's say we're graphing heights. This will be the average height, and heights out here could exist, but they're very unlikely. Heights down here could exist, they're very unlikely. Same thing, we're saying the electron is probably here, could be here, but it's unlikely, could be here, but it's unlikely. That's what psi squared gives us. What is an orbital? To get an orbital, it's 3D space. Where there's a 90% chance of finding an electron. So if I wanted to say, based on this graph, 90% of the heights fall within those two things. Okay, we're going to do the same thing, but in 3D with our psi squared. I'm going to say 90% of the time, the electron's going to be in this region. We put a boundary layer around that 90%, and we call that an orbital. All right, last question. How does the concept of an orbit in the Bohr model of the hydrogen atom differ from the concept of an orbital in quantum theory? So remember, the Bohr model had a nucleus with n levels around it, and now quantum theory says instead of these orbits, we're treating electrons as waves, and we're saying instead of this is where they are, we're saying this is where they're likely to be. So one thing, Bohr, and I'm going to say quantum. Bohr is 2D, quantum is 3D. Bohr treats electrons as particles. Quantum treats them more like waves. And Bohr says where the electron is. Quantum says where electron could be. Those are really the big differences that come to mind for me. How many quantum numbers are needed to identify an orbital? How many are needed to identify an electron in an atom? Why is there a difference? So we'll talk more about this in problem set 10 when we talk about quantum numbers. But you need 3 to identify an orbital, 4, so you need to add another one to identify an electron, because each orbital can hold 2 electrons. So it's kind of like a house. If I'm writing a letter, I need to give like a city and a street and a street address to identify a house. But if I want to actually identify somebody in the house, I also need to put the name. So that's what we're doing. 3 identifies the orbital, but since each orbital can have more than 1 electron, you need a 4th to say I'm talking about this electron versus a different one. And again, if you watch the video for problem set 10, you'll see that broken down in detail. But this is just an introduction to treating electrons and other particles as waves. Hope that helps.